So we can mimic the free coiling activity, the creation of a perversion, and also the behavior of the pulling force. Thanks to these results, in order to reach a design for a biomimetic robotic tendril, we evaluated on one hand literature and on the other hand shape or smart memory alloy behavior, and we developed a simplified model of the tendril. So we divided our tendril in two parts. The first one that is mainly devoted to grasping, the grasping by coiling, and the other, the free coiling, that is mainly devoted to realize the free coiling, so the pulling force. Starting from these two different parts, we try to model from a kinematic point of view the grasping coiling part, dividing it in subsections. So for each subsection we can define our model, kinematic model. So starting from the curvature, from the length, and from the angle of curvature of each small section, we can model with different joints and pairs from a robotic point of view, so universal or revolute joints and the prismatic joint. We can define the dynamic-Artemer frames, so we can explain the dynamic-Artemer notation. We can define the table of parameters of dynamic-Artemer and model the overall kinematics of the tendril, so the motion of the tendril. Thanks to this, we can also implement this model in a simulator, and here unfortunately I cannot show you the video, it doesn't work, but by implementing our model we can show and mimic the main behavior, grasping behavior of the tendril. This is the grasping by coiling part, these are the small sections, and when one of the sections hits the support to be grasped, bends the remaining part of the tendril. So it's a sort of reflex behavior, modular reflex behavior. Each part is sensitive and controls only one joint, and so the rest of the tendril, the remaining part of the tendril. After that, taking into account that our purpose is to exploit shape memory alloy materials, so we want to use materials such as cables or springs in order to move our small section. We developed also a transformation between the dynamic Artemer parameters, so a robotic model, to the wire lengths of each section. So in this case, I put here a figure with two dimension of two dimension. We have two wires, and we developed this model in order to have the equivalence, the transformation between the previous model and the new model. After that, in order to create something that can be used for future prototypes, we tried to define a modular structure in order to have a proof of concept. We work with shape memory alloy nitinol wires, and we create different wires with different memorized shape. On one end a coiled shape, and on the other end a stride shape. So by activating or by heating the coiled shape wires, we can have this kind of behavior. So we can mimic the bending and coiling activity of the tendril. In the other case, if we give current to the other wires, we can recover the original shape of the system. So we can mimic we can emulate the bending and coiling behavior of our tendon. This is one proof of concept. On the other end, we try to define how to design, how to create the different sections of our grasping by coiling part in a simple form, in a simple way, by using springs that can contract when heated or by using wires. In particular, here we have a rigid part with an hinge element, and we have two different springs by alternative. By giving current to the right or to the left spring, we can obtain the motion of the two platforms, and we can mimic the behavior of bending in one and the other direction. The other two pictures can show how to have a single side motion, so only in this direction, or how to exploit wires for creating our single section for the grasping part of the tendon. So we tried to mimic the tendril in order to have by-inspired robotic systems. First of all, we evaluated the grasping and the recoiling activity in order to see how tendrils can grasp by coiling and how their support is recognized. After that, we evaluated why nature evolved in such a direction, in particular why nature has chosen helical springs, and after that we emulated the behavior by means of shear memory alloys, and at the end we designed from a kinematic point of view and by means of proof of concept by simple prototypes the tendril behavior.